Bam! Mr. Tarrou. In this calculus video, we're going to do 5 definite integrals involving improper integrals. The first example is just going to be a pretty straightforward example where the upper limit is infinity. This next example is going to have another upper limit of infinity. It's just going to vary a little bit in the fact that one example is going to be convergent, one is going to be divergent. We're going to look at a third example where the lower and upper limits are both, the lower limit's negative infinity, the upper limit is positive infinity, and we'll have to have a little bit of inverse trig function integration involving inverse trig functions in there, and that'll be add some interest to our problems. We're then going to do 2 more examples where the lower and upper limit is already a constant. Like, it kind of looks like an integral, a definite integral that we should be able to do without this idea of it being improper. But like you'll see here in our little example to start off with, to introduce this idea, maybe the function won't be continuous on that closed interval. All right, and I'll put links to all those examples in the description in case you want to skip ahead and you don't need the whole lesson. So here, let's see. I didn't like my first introduction. We want to find the, with the idea of like, hey, let's find the definite integral from 0 to 3 of 1 over the square root of 2x dx. Okay, that looks very straightforward. But when you look at the function y equals 1 over the square root of 2x, or just look at here, when our lower limit, when we plug that lower limit into this function, we're going to be dividing by 0, and you can't do that. And when you look at the function, you can see as we approach 0 from the right, that function is shooting off to infinity. So really, this function is never going to, it's going to get infinitely close to that asymptote, but it's never going to touch it. And that is a problem. This is an unbounded region. How do you deal with that? Remember that the first fundamental theorem of calculus says that if a function f is continuous on the closed interval, that's what we have a problem with here, and kind of technically with all of our 5 examples, and capital F is an antiderivative of f on the closed interval from a to b, then of course the definite integral from a to b of f of x dx is f of b minus f of a. That condition that, this first fundamental theorem of calculus doesn't work unless you're doing it on a closed interval. And, being continuous and all that good stuff. So what do? We can't find straightforward the definite integral from 0 to 3 of this function because we can't divide by 0. This is an unbounded region. But this function is continuous. Actually, the domain of this function is 0 to infinity, right? And as far as this definite integral is concerned, this is continuous on the open interval of 0 up to the, on the right side. Of course, this is continuous and defined at 3. So we have a partially closed interval. But, maybe we could just say, well, okay, if I can't let my lower limit go all the way to 0, let's let that lower limit go to 0.1. We're continuous on that closed interval. Well, yeah, but this function is continuous, continuous all the way back to 0.01. That would be a better approximation of this area. Well, how about just letting it approach 0.001 or 0.000001? Oh, it kind of sounds like we're learning that the idea, like when we first started learning the definition of a derivative, and we were letting those points get ever close together until we got an exact approximation of the slope of some curving line, an instantaneous rate of change. And that's what we're going to do here. We're going to take the lower or the upper or maybe both limits out that that fail this idea of a closed interval situation, put in a lower upper limit that will pass this closed interval condition, but then with the idea of a little bit of an addition of limits out front, allow us to get infinitely close to whatever those lower and upper limits we're really interested in, but yet take care of that closed interval condition that we have on the first fundamental theorem of calculus. And this is how we're going to do it. This is how we do it. Okay, so get that hung up there without spilling my coffee. This video not brought to you by Yeti cups, but at any rate, the definite Definition of an improper integral with infinite integration limits. If f is continuous on the interval from a to infinity, our first three examples are going to have lower upper limits, which are infinity or negative infinity, then we're going to say, okay, we have a definite integral from a to infinity of f of x dx is equal to the limit. Now we're going to put in an upper limit such that the function is continuous on that closed interval, but then we're going to let it approach infinity. The limit as b is approaching infinity of the definite integral from a to b of f of x dx. If our lower limit is negative infinity, same idea, we're going to put in a nice lower limit that meets that closed interval condition, but then let a, with the idea of limits, approach negative infinity. And if f is continuous on the interval from negative infinity to positive infinity, and we want to find that definite integral, maybe some kind of function that comes along and it's approaching the, say, the x-axis, it's approaching 0 as x goes to negative infinity, kind of rises up a little bit, and then approaches 0 as x goes to a positive infinity. So you can see like the x-axis or some area being sandwiched between the x-axis and the function, and thinking, well, you know, if those values, if those sums go to 0, then maybe there's some kind of actual area under there we can calculate. That's what's going on here. So we're going to split this up and introduce a constant between negative and positive infinity, and then apply rule number 1 and 2 and say, well, okay, my lower limit is negative infinity, so we're going to let the limit as a approaches negative infinity, get some kind of nice variable constant in there. So definite integral from a to c of f of x dx, and then plus let b approach positive infinity, and so we're going to find the limit as b approaches infinity for the definite integral from c to b of f of x dx, and then we're going to just add those two values together. The definite integral converges if you, in other words, you're going to have a real answer through this integration after you finish this integration process if all the limits exist. Otherwise, the definite integral diverges. In other words, we're not going to be able to find, if we're doing like an area problem, what the area is underneath that curve. And of course, every time you do a definite integral, you're not finding area. We know that now. There's lots of applications of definite integrals. So let's get on to our first example right now. Alrighty, example number 1, we're going to find the definite integral from 1 to infinity and beyond of 4 times x to the negative 4 dx. And all my videos have examples that go from easy to hard. That's how you should learn things. So this won't be too terribly difficult. It's just the idea of getting used to this new type of definite integral. Well, this function is not continuous on a closed interval because I don't even have a closed interval. Infinity is, by definition, is an open interval. So we're going to set an upper limit of b and say well, I guess technically we're going to let b approach infinity, but we're going to find the limit as b approaches infinity of the definite integral from 1 to b of 4x to the negative 4 power dx. Okay, so that means we're going to find the limit as b approaches infinity of, this is just a power rule, take this power, raise it by 1, so we're going to have x to the negative 3rd. Of course, with integration, we have to divide by that, so we're looking at negative 4/3. And now our upper and lower limit. Plug those in. And now that we have finished the integration, the only thing we have left to do is let b approach infinity. And when we do that, of course, when you have a fraction in the numerator and the denominator is just expounding until, to infinity, that is going to approach a value of 0. And we have 0 plus 4/3, which is equal to 4/3. And so because through this process we created a limit, and when we finished we got a real answer, that means that this limit converges and our answer is 4/3. So this is a convergent limit. Okay, so over here we have an example that's very, very similar. So let's work that out and see what happens. Now at this point, everything's going quite swell. We're going to let b approach infinity. Don't really know why I wrote 1 to the 4/5. It's 1. And look what's happening. When we let b approach infinity, this first term in this binomial is going to infinity, and we have infinity minus 5/2, which just means that this is going to keep getting bigger and bigger and bigger as b keeps getting closer and closer to infinity. So this limit comes out to be infinity minus whatever, and still comes out to be infinity. So this limit is let's try that again, divergent, and it doesn't exist. So we cannot work out this definite integral. It has no real solution, it's just infinity. Whereas over here, we were able to, by letting b replace that upper limit of infinity and setting up some limit notation, actually got a direct answer of 4/3. So if we graphed, y equals 4 times x to the negative 4 power, and if it was just an area problem, from 1 off to infinity, as that graph, I'm sure, is going to be approaching the x-axis from above, approaching 0 from above, that total area bound between the function and the graph, the function and the x-axis would add up to be 4/3. All right, let's work on to our third example involving some integration involving inverse trig functions, and just makes it a bit more interesting in the fact that it is a trig function, and the lower and upper limit are both going to be some form of infinity. Example number 3, we're going to find the definite integral from negative infinity to positive infinity of 4 over 36 plus x squared dx. Okay, well, our lower and upper limits are both infinity, and like our note showed, we're going to go ahead and split this up by introducing a constant in between these lower and upper limits. And now we're going to go ahead and introduce that limit notation so that we can satisfy that closed interval requirement that we have for the first fundamental theorem of calculus by introducing a lower limit of a and letting a approach negative infinity, and an upper limit of b and letting b approach positive infinity. I need some kind of constant in between negative and positive infinity, and let's not write c and have a bunch of variables. We need a concrete constant between negative and positive infinity, and I'm probably going to guess that the easiest constant to work with is 0, which is what I really meant to write. Excellent, excellent, excellent. Now, at this point, we have a pattern, an integrand that I hope is starting to look rather familiar because we've done a lot of this lately. This is an inverse, basically a pattern that is going to result in an answer, which is an inverse trig function. That is, when you integrate du over a squared plus u squared, that is going to be equal to 1 over a times the arctangent of u over a plus c. So I'm going to, just to make sure this comes out to be nice and neat when I'm done, because this is not a super long problem, but I only have a 4x8 board to fill up. I'm going to step off, and maybe you can pause the video now and see, if you can finish this on your own. There's not too much that's tricky with the rest of this problem, just, working with that integral involving inverse trig functions, and maybe knowing a little bit of your unit circle and what the graph of tangent looks like as you near the end of the problem. So pause it, try and finish it yourself. And for inverse trig functions, you're putting in an angle measure. So arctangent, did I just say angle measure? Just to make sure this is perfectly clear, I said that was an angle measure, so I'm reshooting. Okay, so we went through this integration process, moved the 4's out front. Both of these terms had a coefficient of 4, so we factored that common factor out, worked through that integration and got the inverse tangent function. And then ultimately, just to make sure you understand what's going on as we finish this this question, and get close to the answer, I've graphed the center period for y equals the tangent of x, just reminding you that it does pass through the origin 0, 0, and as it approaches pi over 2 from the left goes to negative positive infinity, and as you approach pi over 2 from the right, it goes down to negative infinity. And when you work with trig functions, you put in an angle measure and you get out the sides of a right triangle. Well, with inverse trig functions, you're putting in that ratio, in this case, of y over x, and you're looking for an angle measure in return. So if your y over x ratio is going to negative infinity, what angle measure are you approaching? That looks like negative pi over 2. So, and again, it's about, and really my notation isn't really exactly correct here, right? We're letting a approach negative infinity, so really it's about, you know, what is the arc tangent give you as an answer as the angle measure approaches negative infinity. Of course, tangent is undefined at negative pi over 2 and positive pi over 2 for that matter. That's why it's going off to infinity. But, so we have 4 times negative 1/6 times negative pi over 2 plus 1/6. And we're looking at, as we approach, you know, what's happening is we're approaching infinity, we're approaching the angle of pi over 2. So we are looking at a negative 1/6 times a negative 1/2, basically giving us a positive. So we have 4 times, well, pi over 12 plus pi over 12. You see we're getting to a real answer here, so this limit's converged, or is convergent. And we get 2 over 12, which is pi over 6, and 4, you know, times pi over 6 is ultimately going to come out to be 2 pi over 3. That real solution, and so this limit converged, and we are done with our third example. Now, what happens, like that first little example I had on the green board, where the lower and upper limits are constants, and it looks like a definite integral that we should be able to work, unlike these where we had lower and upper limits of infinity, which was definitely the first time we saw that. Well, let's get our notes out of the way and do those last 2 examples. Second day of recording here at Prof. Rob Studios, and our second page of notes. Definition of improper integrals with infinite discontinuities, like that sketch that I had on the green board at the beginning of the video, where that function was going up to positive infinity as we approach 0 from the right. So if f is continuous on the interval from a to b, where it's closed on the lower limit of a and open around the upper limit, and has an infinite discontinuity at b, then we have the definite integral from a to b of f of x dx is equal to the limit as c approaches b from the left. Now, of course, if b is your upper limit, we're going to be, you know, approaching it from the left-hand side, and that function is going to infinity or negative infinity. Yeah, so we're going to put in a constant there, or a variable c, let it approach b from the left-hand side, and we have the definite integral from a to c of f of x dx. If f is continuous on the interval from a to b, open and closed, and has an infinite discontinuity at a, that lower limit, then the definite integral from a to b of f of x dx is equal to the limit as c approaches a from the right. It's a lower limit. We're going to be approaching it from the right, of the definite integral from c to b of f of x dx. Now, if f is continuous on the interval, the closed interval from a to b, so it's looking like we have that, you know, we have that closed interval requirement, of course, but one of the most important thing is it's continuous on the closed interval, and it turns out that there's some value of c in the open interval from a to b. That notation is saying that our value of c, where we have this infinite discontinuity, isn't one of the endpoints. Otherwise, we'd be dealing with section 1 or 2 up here, at which f has an infinite discontinuity. Then the definite integral from a to b of f of x dx is equal to the definite integral from a to c of f of x dx plus the definite integral from c to b of f of x dx. And now see, we have our infinite discontinuity at c, and so we're basically going to then apply rule number 1 and rule number 2 to finish up that problem. The improper integral on the left diverges if any of the improper integrals on the right side diverges. Otherwise, if both of these converge, then of course you have a real answer for whatever your definite integral is on the left-hand side of the equation. Our last two examples are going to be dealing with these type of improper discontinuities. Actually, we're going to be involving parts 1 and 2 here, and you'll see that these examples are definitely going to be more involved than our first 3. Bam! So for our fourth example, we have the definite integral from 0 to e squared of the natural log of x cubed dx. Okay, well, we took the derivative of the natural log of x. That was just simply 1 over x, but there's no basic integration rule for integrating the natural log of x. So this is going to be, like I said, a little bit more involved. We're going to start by expanding the logarithm using the power rule like we would have done when working with derivatives. So we're going to have the definite integral from 0 to e squared of 3 times the natural log of x dx. And why is this example in this video? Because, well, y equals the natural log of x. We know now that when you take the natural log or log of any number, you get an exponent. And the base of logarithms, by definition, must be positive, and you can't raise a positive number to any power and get a negative answer. Thus, you can't take the log of a negative number, and our function looks something like this. So this y equals the natural log of x is not continuous on this closed interval. There's an infinite discontinuity. So we're going to what? We're going to go ahead and, okay, it's that lower limit. We're going to be approaching 0 from the right. So we're going to say let the limit as a approaches 0 from the right of a to e squared of 3 times the natural log of x dx. Awesome. Okay, well now let's worry about actually getting this integration done here. I'll probably have to erase this later. I know we're going to need, without that basic integration rule for the natural log of x, we're going to try and work through the integration by parts to help us finish this problem. So I'm just going to kind of do this sort of off to the side, but I've only got the one board to work on. So we're going to work on the integration by parts, which says, just in case you all need to see this one more time. Never hurts to keep working through those, writing those down and saying those formulas and rules over and over again. When you do an integration by parts, and we're going to be integrating, of course, 3 natural log of x dx, you're looking for the factor of that integrand, the most complicated factor that can be integrated using a basic integration rule. Well, I just said there's not one for the natural log of x, so we're going to need to focus on that 3 dx. And so dv is going to be 3 dx. Integrate both sides, and we have v is equal to 3x. Now, the remaining part of our integrand is going to be something that hopefully when we take its derivative, we get something that is simpler. And so u is going to be equal to the natural log of x, and so du is going to be 1 over x dx. Okay, so where are we at right now? That means that the indefinite integral of 3 times the natural log of x dx is equal to uv. So we have uv, 3x times the natural log of x, minus the indefinite integral of v, which is 3x, du, which is 1 over x dx. Okay, well, we can see these. We have an x effectively in a numerator. So, of course, those are going to cancel out. And we're just simply integrating 3 with respect to x. And so we have 3x times the natural log of x minus 3x. Awesome. So going back here, we basically, we did integrate 3 natural log of x dx, and we got 3x natural log of x minus 3x. So we're looking at the limit as a approaches 0 from the right of 3x natural log of x minus 3x with that upper limit of e squared and lower limit of a. Okay, well, let's go ahead and get those upper and lower limits plugged in here. All right, now 3e squared natural log of e squared minus 3e squared, we plug in that constant. This is all just a constant. And really, when we let a approach 0 from the right, that's obviously just going to be going into the second grouping over here. So let me clean this up a little bit. And the natural log of e, those are inverse math operations, so they're going to cancel out. So all this just becomes as 2, and we'll have 2 times 3. Okay, so 6 minus 3 is equal to 3. And if we let a approach 0 from the right, we're going to have 3 times 0. The natural log, what is the natural log function doing as a approaches 0 from the right? The natural log function, as you approach 0 from the right, is going down to negative infinity. And then we have 3 times 0. So really, anything times 0 is 0, and all this cancels out, and our final answer is going to be 3e squared. Not quite just yet. That may be the answer, it may not. But right here, let's see, am I going to pick a different color? Right here, 0 times infinity is a form of indeterminate. We're not guaranteed that that's actually equal to 0. We need to go back to L'Hopital's rule. And that means we're going to focus on the side here, the limit as a approaches 0 from the right of 3a natural log of a. And we just discussed, that comes out to be 0 times negative infinity. That's an indeterminate form. And so I don't really know what the answer is. What we need to do is remember with L'Hopital's rule that, we need to, if it's not already, get that indeterminate form into either something like 0 over 0 or some form of infinity over infinity. So we're going to change this 3 times a over 1 to be a division of, we're always talking about when you divide by a fraction, you flip it up and multiply by the reciprocal. We're going to do the opposite of that. Instead of multiplying by a number, we're going to divide by its reciprocal. And that's going to give us the limit as a approaches 0 from the right of, let's see here, 3 natural log of a over 1 over a. And now when I let 0 approach 0 from the right, we're going to have 3 times negative infinity, which is going to be negative infinity over 1 over some value approaching 0 but positive, is going to mean that this bottom value is going to approach positive infinity, which is still an indeterminate form. But now that it's that infinity over infinity, we can take the derivative of the numerator and the derivative of the denominator separately, applying that L'Hopital's rule, and see if we get an expression that will allow us to plug in 0 and actually find out what this limit is equal to. So we have the limit as a approaches 0 from the right. Again, we're applying that L'Hopital's rule, so the derivative of the natural log of a is going to be 1 over a. And our denominator, this is really just sort of, what? A to the negative 1. So you bring that negative 1 down and reduce the power by 1, so we're going to have negative a raised to the negative 2 power, or negative 1 over a squared. So we've taken the derivative of the numerator and the derivative of the, I said numerator, right? And denominator separately. Let's clean this up. Let those common factors cancel out. And now we can see that if we let a approach 0, not add to it. When you let a approach 0, then indeed this actually is going to come out to be 0. So don't get lazy, don't get complacent. Make sure that you remember all those different forms of indeterminate. And in this particular case, not all the time, 0 times this negative infinity, well, that's not really 0, but we've proven it through L'Hopital's rule that that limit does actually approach 0. So we have 3e squared minus 0 plus 0, and this is the final answer. This is a real value. This limit does converge. And let me just make sure I didn't say something silly. Nope, that actually, oh, wait a minute. Yes, that is correct. So that is the end of our almost last example. Got one more coming up right now. It's our last example. Example number 5. We have the indefinite integral from 3 to 9 of 1 over x squared minus 9 dx. And this is another example where we're going to have an infinite discontinuity at 3. If you plug 3 in, you get 3 squared, which is 9. 9 minus 9 is 0, and you can't take, well, you can take the square root of 0. Almost misspoke there. But you can't divide by 0. And so in that way, this example is similar to the previous one, but I'm just making sure that, as I go through these assignments and relearn these concepts on my own and prepare for these lessons for YouTube, that, I'm picking out these questions that keep reapplying these techniques that you learned just in the fairly recent past sections. And yes, I haven't, I've been teaching for 20 years and I teach calculus now in my high school, but I'm using you guys as an opportunity to go beyond the concepts that I teach in my high school and just sort of put myself back to school and relearn these concepts that I had over 20 years ago in college myself. I said myself twice, now 3 times in the same sentence. At any rate, this almost looks like an integration problem involving inverse trig functions. The indefinite integral of du over the square root of a squared minus u squared comes out to be the arc sine of u over a plus c. But our constant isn't first, we have a variable first. So to do this problem, it's going to involve trigonometric substitution. And that's why I picked this example, or made this example up. When you have a square root of a sum or difference of squares, unless it's like an example I just talked about where it falls into one of those inverse trig function formulas or integration rules, you're going to need trigonometric substitution. And when you have a square root of a difference of squares, that means that this is representing the length of one of the legs of your right triangle. So we're going to need a trig substitution. So we're going to set up a little right triangle, and I don't want to change the lower and upper limits on this indefinite integral. So we're going to go through integrating that indefinite integral and kind of do some sort of side work, and then come back when we're finished and get everything back in terms of x and go back to those lower and upper limits of 3 and 9. Well, we have theta here, and this means that identifying everything that's going on here, that means sort of like our u is equal to x and our a is equal to 3. And one more time, when you do these trigonometric substitutions, you want to set up a primary trig function, a sine, a tangent, or a secant, where the constant is going to be in the denominator. So where does the x and the 3 go? This is representing the length of a leg. The first term obviously needs to be the biggest, so our hypotenuse is definitely going to be x, and so does the 3 go here? Well, if the 3 is here, that would be what? The cosine of theta is equal to 3 over x. Okay, well, I just did that example, and 3 wasn't the denominator, so it could be what? Secant. Secant is r over x. Secant doesn't start with co, like cotangent, cosine, cosecant. So let's put the 3 here, and the square root of x squared minus 9 on the vertical leg. And we have that the secant of theta is equal to x over 3. That means that x is going to be equal to the 3 secant theta. Dx is going to be 3 secant theta tangent theta d theta. And already when we look at this off to the side, and maybe I'll use a different color, the indefinite integral of 1 over the square root of x squared minus 9 dx. So far, we just have substitution to get rid of that dx. We need another substitution to get rid of the square root of x squared minus 9. You also want to have this come out as simple as possible. So you want to set up a trig function that one more time puts the constant in the denominator. So that's going to be the tangent. Great. So we have the indefinite integral. Dx is 3 secant theta tangent theta d theta. Square root of x squared minus 9 is 3 tangent. The tangents cancel out. The 3's cancel out. This comes out to be the indefinite integral of secant of theta d theta. The integral of secant theta is the natural log of the secant of theta plus tangent of theta. Absolute value. Now, when doing the scratch work for this idea of this indefinite integral, of course there is a plus c, but we're not doing an indefinite integral. We're really working on working out that definite integral. Plus c? Mm-hmm. Yeah, okay. But at any rate, yes, when you do indefinite integration, don't forget about your constant integration, but we're just setting up to work with that definite integral. The secant of theta, now I want to go back up into here. I want to remove all those references of x, so the secant of theta is, well, right there, x over 3. And the tangent of theta is the square root of x squared minus 9 over 3. So now we're looking at the definite integral from 3 to 9 of 1 over the square roots of x squared minus 9 dx is equal to, well, we did just integrate, right? I integrated the indefinite integral, so it is equal to, yes, let's not forget the limit notation. So we're going to say the limit as a approaches 3 from, this is the lower limit, so we're going to be approaching it from the right, of a 9, 1 over square root of x squared minus 9 dx. I am prone to making small mistakes, especially now when I'm talking to the camera and trying to think and write at the same time. Maybe I should check my work, make sure I haven't really done something silly. What did we get down here? Yes, and we're going to clean up this whole fraction thing here in a second. Actually, since I just reminded myself of it, I was going to do it up here, but this is going to be equal to, okay, now let's see here for a second. We have the natural log of 2 terms being added together, and we have a common denominator of 3. And maybe I got rid of that plus c a little bit early. This is going to become just a big ol' x plus the square root of x squared minus 9 all over a common denominator of 3, and expanding that logarithm like we've already, like I did in the previous example and like we did when we did derivatives. This is going to become the natural log of the absolute value of x plus the square root of x squared minus 9 minus the natural log of 3 plus c. And well, this will be a little bit easier to work with, and the natural log of 3 is a constant, plus a constant just gives me another unknown constant. So this is all just going to be a new value of c, which again, we don't need to be concerned about because we're not really doing indefinite integration. So now that we've got our limit notation in here, and we've satisfied, that continuity that we need in a closed interval for the first fundamental theorem of calculus, we get the limit as a approaches 3 from the right of this. That's why I check my work. That's plus That's minus. One more check. Natural log of 3 plus 2 square root of 2. You know, you would think after 20 years of teaching I would stop making little sign errors and small stuff like that, but we're all human. We all do it, and I definitely do it more often than I would like. That is the end of our last example, and I hope this helps you now how to deal with improper integrals. I'm Mr. Tarrou. Bam! Go do your homework.